but the Indonesian government charges money. Yeah, see? I need to talk to Leo. Call
Nih,
this
boleh
bitches.
bagian apa? Leo.
Yeah. Oh, tell them call these bitches.
Tell him when he comes.
Bro, that's a hard miss, man. You get free accommodation, free transport, free food. You just need to pay your ticket and visa. That's it. You get everything else, bro.
You're basically like being scammed like $50 or so.
Yeah.
And you know, for me, yesterday I went to Cikarang to search for living
The accommodation. Yeah.
It's all full, man. Like at Richard's chosen apartment is
Bro,
full.
just stay in a hotel, man. It's cheaper.
For 2 months.
Yeah. Bro, imagine you're staying in a hotel. You don't need to pay for Wi-Fi. You need water, electricity. You don't need to pay. You have cleaning services, and then you get laundry. Yeah, you just can call or something else. And then you get free breakfast in the morning. You get food.
Yeah.
Bro, if you take all of this into consideration, it's cheaper to go in a hotel. Yeah, it is cheaper to go in a hotel.
Yeah,
2 months. Hi.
a day in a hotel is like what?
300.
300k, 400k.
Depends lah.
What do you mean?
Bro, it's still cheaper. Bro, I searched on
You know what my
Airbnb.
mom said? Like, rather than going to ACME, she
Yeah.
would rather make me go to China with you.
Yeah. No, China I'm going January.
Yeah, no, but for
I was
us, me,
supposed
like, my mom would rather me going to China because my dad has connection there. Like, for like machining and stuff like that, in China they have, like, in New Way, Shenyang, like they have.
Yeah, right now this one's supposed to go to Suzhou Industrial Park. They have connection over there.
My dad's in Shanghai and Guangzhou. I think.
What does your dad do? Business import?
Yeah, selling machine.
Oh, what kind of machines?
CNC, laser, torque punch.
Wow. Sir, question.
Yeah.
Yesterday, our lecturer sent something about going to China program for 4 weeks. But the portal already closed the same day, and the deadline is today. Like, is there like a way? I don't know.
What
maybe,
portal?
to register.
Like Google Form?
It's a Microsoft Office phone. Yeah.
Okay.
It's closed.
Contact Bu Yunita,
Uh,
head of study program.
yeah, but the form is not for SGU. It's like the ICC form.
Oh,
The deadline is today. They put a QR code deadline 30 April, but it closed yesterday. So there's a couple of friends we want to go, like 3 or 4 friends.
yeah. Why don't you go to Bu Yunita? I think she can help you out with that.
Okay.
kalian pikir isi VT di mobil Honda?
Trying to find the video that I watched before. Okay. That's it. All right, so let's start our 2-week series on hybrid and EV systems. Today we'll talk about just general overview, traction motors, hybrid systems, and then next week we'll talk about batteries because that in itself takes a lot of details on that, right? So let's dedicate battery systems next week. Okay. Now, composition of EVs. Of course, you know that hybrid and EVs kind of go hand in hand because we started with hybrids. I don't know, 2003 Toyota Prius. A friend of mine bought it the first time it came out. It was pretty interesting, and he also hacked into the system. You can show how much is being consumed where and all that. It was really fancy at the time. And I think the hybrid Synergy drive already came out at that time. It was very, very revolutionary. So, different types of hybrids that we see here, right? Plug-in, full hybrid, plug-in hybrid, battery, meaning full EV, no gasoline engine at all. Fuel cell is really, really small. I don't know. I just don't think fuel cells going anywhere. And there are some hydrogen proponents that are really, really loyal. But are you believe in hydrogen, right?
Yeah.
Yeah.
It's definitely going to be, I guess, the future.
It's-
My opinion.
Yeah. It is a conversion thing, and it's just the scale. You need to get to a certain scale in order to.
I think it's just about efficiency right now.
Unless the government is really, willing to invest and make the push for it.
I think only China is doing that.
It's very hard.
They need to make 5,000 cars by the end of next year, I think, with fuel station also.
Yeah.
So,
So, but today we'll be talking about gasoline and electric hybrids, not fuel cells. So you see the trend toward BEV because, the big reason is just practicality and less dependent on oil, the global politics today. I think psychologically people are just sick of it. And, let's just keep it neutral, not this aggressive dependency on oil. But BEV is driven mainly because of battery costs, right? Battery costs sloping down constantly. We are getting into solid state batteries also, but that's next week. Now, you see the transition also, right? A mild hybrid would have a small battery, like tiny. Basically the battery is only for regenerative braking. You can think of it that way. And I think a few folks are doing a hybrid conversion for the cart, for their thesis. And I told them you have to have regenerative braking, otherwise, what's the point of having it hybrid? So even mild hybrid, you will have a regenerative braking. That's how hybrid actually started off. The rationale for hybrid didn't begin with a cheap battery, it didn't even begin with motor performance. It began with regenerative braking. I mean, the logic is such that you burn your gasoline to get kinetic energy, and then when you brake, it just goes into thin air, right? Your energy, what you paid for, just evaporates as heat on your brakes. So that was the first motivation, the original motivation for hybrid. Hey, how do we capture that back, right? And once the battery starts to kind of make sense, and the first hybrid is still NIMH, actually nickel metal hydride, which was still the original, like rechargeable battery. You remember that in your, I played Tamiya a long time ago. So we use rechargeable batteries, and that's NIMH battery. Has some memory effect, not as good as lithium. You cannot extract that much current out of it instantly, but it was the original one. So a mild hybrid regenerates and helps you accelerate off the line, and then the battery will be gone in no time, right? You cannot operate on that battery. And then you got the full hybrid. The full hybrid, then you use the traction motor to actually accelerate, and you can operate on the traction motor alone for city driving and slow speed driving, stop and go traffic, right? And the battery, you need a better amount there. And then you get into the plug-in hybrid, which I don't know. I'm not sure that classification is getting more and more ambiguous this time around. Like, if you look at Honda HEV systems, they basically, if you do mostly city driving, you're basically on a series hybrid most of the time. So you basically use the gasoline to charge the battery and reuse the electricity, just like Nissan e-Power. So in that case, I mean, the gasoline, I don't know whether you would call that plug-in hybrid. I guess plug-in hybrid by definition is something you can plug in, you can charge if you want to go on low gasoline. And then you got the battery electric, where you charge and that's it. You have to charge. There is no gasoline tank, right? There is no gasoline engine at all. I think we're heading toward this or this, right? I mean, for ecosystems in which charging infrastructure is still bad, with batteries getting cheaper, motors getting mainstream, we are heading toward these too. And so the batteries we're talking about is in the range of 30 to 200. I think most passenger cars will be in the range of 60 kilowatt hours. Like Ioniq 5, I think have 70 something. Atto would have something like 50 something kWh. Okay, and it's getting cheaper. The e-motor, I don't think, 150 kilowatt is already giving you a good amount of acceleration for passenger vehicles. That is equivalent to like, 180 horsepower. Yeah. So that's already good. Now, let's discuss like an EV overview before we get into the motors, and then we'll get into hybrids. All right? So,
electric cars are making big waves in the automobile world. These stress-free pollution.
this is from 8 years ago, and this was Tesla. Of course, Tesla was the pioneer for this. And so some of these technologies even already outdated. Tesla Model S, I think, still use somewhat, I think they still use induction motor at the time. NCM battery, nickel, cobalt batteries, but nowadays they are even shifting to LFP, the Teslas. But here's the battery systems, right? This just gives you a good overview, right? So you got the motor, you got the induction motor. Nowadays, most EVs use PMS, permanent magnet synchronous motor, okay, PMSM. An induction motor does not have permanent magnets. We'll talk about that. And it's basically a squirrel cage motor, a three-phase, just like an industrial motor actually. So you excite that on the stator. You have this rotating magnetic field which induces a magnetic field in that cage, in the rotor, and then the opposing magnetic field then kind of. You can think about this like, if you notice like in a football stadium, people cheer with waves all around. So I mean, think of it that way, right? I mean, this wave going around in the stadium, and then you in the middle, as the football player, kind of follows that wave, right? So think of it like that. So there's always a delay. There is some inefficiency in this motor, but it's pretty good. It's pretty good. You can get up to like 85–90% of this. In replacement of a gasoline engine, where you have this power band that is very limited, and that's the reason you need transmissions, right? The reason you need transmission is not because just because you need to reduce the RPM, but you need shifting mechanisms, because you can only get so far. Otherwise, you'll have a single-speed transmission, which we do have in the EV. So imagine you get rid of this chunk of steel. I mean, that's a lot of weight saving, but then you have your batteries. So all these are gone. You just have a single motor, huge power band up to 18,000 RPM. That's a lot of speed. I mean, you need a lot of balance on that, manufacturing. Now, but compared to with an ICE engine, you see the motion that is up and down. You got a lot of balance issues here, right? You need the flywheel to stabilize the power generation. It is a huge simplification to simply change that just to electric motor. So it is a huge change. Okay, look at the weight to power ratio. So the power produced per weight, you got 180 kilograms on a typical IC engine, producing 140 kilowatts. You got the Tesla induction motor, 31 kilograms producing 270. Now, you do have the inverter, and to ruin everything, you got the battery. And so you end up with something even heavier. But if you talk about the powertrain itself, sure, you win. Okay, you got a huge battery pack, and you're going to need a inverter to actually control it. You got a lot of cooling needs to be done on the battery, on the inverter, and on the motor itself too. But depending on the type of motor, you might not need that much cooling. In a permanent magnet motor, the rotor does not need to be cooled that much. The stator is the main cooling area, and it is much easier to run coolant around the stator. To run coolant inside the rotor is more tricky and suspect to leaking. But yeah, you need to cool down the battery. The inverter not as much, but yeah, needs some cooling. The job of the inverter is to change from DC to AC. I don't know why they call it an inverter though. I guess a converter would be AC to DC, and that's why they say it's an inverter. But you know that the inverter in a EV is also doing an AC to DC conversion. right? Because you have regenerative braking, so you have to do both ways. So the inverter is not just DC to AC, it's actually both ways. You got the coolants cooling down the battery. There is a crucial limitations actually, especially when you dump all the power from the battery. Okay, so you need good cooling there. That is a big part of the battery systems. In fact, fast charging is also limited by thermal limitations. So the key in fast charging is actually cooling. You got huge packs. The BYDs come up with blade batteries. We'll talk about that next week. Okay, so getting those coolant heat out. Not as hot as your engines though. Yes, it's hot, but it's not. The amount of heat is not as much as an engine. Because an engine, you literally burn gasoline, right? Nice center of gravity for EVs. That will help with the roll. The amount of roll and everything is just better. The closer you are to the ground, better. And it does provide some structural support. Okay, it's usually single speed. Yeah, just gear train, no shifting. You can do reverse too, obviously. Nice. Okay. Now, they use open differential because you can manipulate any slip or any need for handling these, what do you call it? If one slips, then you reduce the torque on the other side. You can actually control your brakes independently. And so if you brake on the slipping wheel, you also produce torque here. So you can do that. The other thing, if you have independent motors on the rear, you can do torque vectoring. That's really nice. So you basically accelerate the right wheel more than the left, and you can actually change the vehicle dynamics. Oh yeah, yes. So you can actually brake the slippery surface with individual braking, and therefore it will transfer torque that way. Not so with gasoline engine, it's more complicated because the response is not as fast. Of course, regenerative braking is always active. In this case, it works as a generator. You can also do a one-pedal driving with an EV. Not all EV have this, but it's really nice. I tried my friend's Ioniq 5, and you basically never step on the brake, unless emergency, of course, and you can still do that. But you can actually let go of the gas pedal up to stop. So you let go of the gas pedal, it slows down using regenerative, and then when it's closer to stop, then it applies your brakes for you. Really nice for this traffic, crazy traffic nowadays. Yep, so regenerative braking, basically it serves as a generator. Okay. Now, let's talk about the different types of motors and the layouts. Let's listen to this one. Wow, where's way?
Uses a single or dual motor setup. The wheels are directly connected to the motors by eliminating transmissions.
The Model S Black and the Tesla Roadster come with a 3-motor setup. 2 individual motors drive each of the rear wheels, and a common motor driving the front wheels.
So, now, we'll talk about the pro and cons between the two types, the two main types. Well, there are 3 main types, but BLDC BLDCs are not present in cars because they have this whining sound. So you got BLDC, you got PMSM, and then you have induction. Now, induction motor is like industrial motors. They are good, not as efficient as PMSM. The torque not as good on low RPM. BLDCs are the predecessors of PMSM. They both have permanent magnet inside the rotor, and they are excited in the same similar way, but slightly different. Now we are down to these two. Okay, this only exists in motorcycles, like in electric motorcycles, because there is this humming sound. Of course, in motorcycles, who cares, right? Because you cannot even hear the sound with all the road and the wind. But inside the car, you'll hear that sound. I think the cheapest Wuling still uses BLDC, and that's why if you're on the outside, you'll hear this whine, this humming. It's really bad. At least the cheapest one that I know of, not the more expensive ones. But nowadays we're down to these two, and I think like 80% of EVs these days are permanent magnets. Okay. Teslas use both. So I think they use, if I remember correctly, they use permanent magnet on the back for the main driving and induction on the front when you're going on a high speed. Because PMSM will suffer more drag in high RPMs because of the back EMF and all that.
The Rivian R1T and R1S has a separate motors for each wheel, however they are inboard and not hub motors. This setup will increase the agility and handling of the vehicle. Before getting into these motor configurations and details, let's understand how an electric motor works inside an electric car. An electric car motor works using a physical process that consists of using a current to create a magnetic field at the fixed part of the machine, called different types of electric motors used in the automobile industry. When it comes to electric vehicles, there are 7 types of motors, with each having its own strengths and weaknesses. They are brushed DC motor,
Okay,
brushless DC motor.
nobody uses this. That's not true. Brushless, BLDCs.
It is a DC motor with permanent magnets. It is called brushless because it does not have a commutator and brush arrangement. The commutation is done electronically in this motor because these motors are maintenance-free. They have traction characteristics like high starting torque, high efficiency around 95 to 98%, and are suitable for the high power density design approach. Brushless motors are the most preferred motors for electric vehicle application due to their traction characteristics.
At least at the beginning. So here we're talking about efficiency-wise. Both of these are way up in the 95%. Here we're talking about 85, to 90%. Okay, slightly less. But it's even worse in low RPM.
These are useful for use in small cars requiring a maximum of 60 kilowatts of power. The disadvantages are a short constant power range, decreased torque with an increase in speed, high cost because of permanent magnet. Cars like Toyota Prius used a brushless DC motor. In this motor, there are permanent magnets on the rotor. Like brushless DC motors, these motors also have traction characteristics such as high power density and high efficiency. Permanent magnet synchronous motors are available for higher power ratings.
So PMS, higher power than BLDC, because BLDC is an older technology, slightly cheaper. The stator are also wound differently, but they are physically very similar, right? I mean, permanent magnet in the rotor, and stator excited with a rotating magnetic field.
It is also expensive as compared to other motors. The advantage of this motor is that it can operate in different speed ranges without using a gear system. It is efficient, compact, suitable for in-wheel applications. It also has high torque even at very low speeds. The disadvantage is that the huge iron will lose at high speeds during in-wheel operation. Most automotive manufacturers use these motors for their hybrid and electric vehicles. For example, Chevrolet Bolt EV, Ford Focus Electric, Nissan Leaf, and BMW i3 use permanent magnet synchronous motors for...
But most do. Like, I think most of the BYDs these days, they're all PMSM, Ioniq 5s, yeah, most of them.
propulsion.
The thing is, in city driving, you don't get up to high speeds for a long time. But in the US maybe, but in Asia, you don't do that much highway driving for a long time. And so it just makes more sense. That's why you also see worse efficiencies in high speeds in many EVs, because it's permanent magnet synchronous. This
Induction motors do not have a high starting torque like DC series motors under fixed voltage and fixed frequency operation. But this characteristic can be altered by using various control techniques like vector control or field-oriented control methods. By using these control methods, the maximum torque is made available at the starting of the motor, which is suitable for traction application. Squirrel cage induction motors have a long life due to less maintenance. These motors can be designed up to an efficiency of 92 to 95%. The drawback is that it requires a complex inverter circuit, and control of the motor is difficult. Induction motors are the preferred choice for performance-oriented electric vehicles due to their cheap cost. Tesla Model S is the best example to prove the high-performance capability of induction motors. Toyota RAV4 and GM EV1 also use this motor.
Okay. We can skip ahead and just do the different configuration.
To understand the single motor system, full motor powertrain, and four motor powertrain.
So, there are these configurations, right? You can do dual motors, you can do single motor, dual motor, triple motor, for four motor. Four motor, probably the big application or advantage is when you're doing off-roading, because then you can really do very good torque factoring.
Let's start with single motor configuration. It's relatively simple to understand the single motor system. There is a single motor that drives the car. There is also a differential as well that allows the wheels to rotate at different speeds. The motor converts the electrical energy received from the battery into mechanical energy, which enables the vehicle to move. It's relatively clear that a car with two motors should be able to offer more horsepower behind the wheel. The combination of the torque from both motors ensures that there is a significant boost in acceleration for the driver. It is important to note.
I think dual motor is mainly done for all-wheel drive purposes. Like, because you can pack a big motor. It's not like it's that limited. You can pack a big motor in one axle, but it's just you don't have all-wheel drive. So, if you want all-wheel drive, then you do dual motor.
Note that the same is also true for a single motor electric car. However, a dual motor is going to outperform a single motor in terms of efficiency and speed at a higher altitude. With the AWD system and the dual motor, the car is able to distribute the horsepower and maximize the torque levels in immediate response to the road conditions. In this system, two motors are provided one on each axle and are coupled through planetary gear, and the torque is coupled through shaft fixed gear. Front and rear motor drives are supplied by one or sometimes two different battery packs. By using two-motor, two-axle configuration, it is possible to choose different power and torque sizing for the drives, and also to adopt different gear ratio for the gearboxes. You can check out, in this system, one motor is being placed on the front axle, while two motors fitted to the rear axle, thus making the car all-wheel drive.
Now, for triple motor, the main purpose is torque factoring. Okay? It's the ability to actually handle the vehicle dynamics independently, left and right. So this is mainly on performance cars. here it is.
Control, something that will make consumer EVs safer and more energy efficient. For motors means proper torque vectoring. Usually, as you turn a corner, the inside wheel and the outside wheel are rotating at the same rate. With torque vectoring, the outside wheel can get more power, pushing the car into a sharper, tighter turn.
So that's what's beautiful about torque vectoring, right? You can literally put however much torque where you want it and where you need it. You can actually steer the car that way.
An EV with 4 electric motors can also be faster and more responsive, as it is adjusting torque electronically by how much power goes to each motor rather than mechanically. Things get even more flexible if you use 2 electric motors for each pair of wheels rather than one. That way, you can use 2 smaller motors rather than one big one.
Okay, so now let's look at a bit more further into the contrast between these three. Okay. Well, I already mentioned some of these, so no need for that. What I want to show you in this video is the physical differences, because it has a nice tear down of the motors.
Physical differences between these two motors. In the case of the permanent magnet motor, the rotor has permanent magnets. This is the interior permanent magnet rotor.
Okay, so this is the shape of the rotor of a permanent magnet synchronous motor, PMSM. What you do is actually you put the neodymium magnets here, okay? And the critical part is how to constrain the stresses on this rotor, because they will be under a lot of stress. And the biggest stress is actually here, right there. That's when it is the most prone to cracking. So you see, this is the neodymium magnets. Anybody ever played with neodymium magnets? It's a really strong magnet. It's not that expensive if you buy small pieces, but just for fun. Sometimes I for the magnets that sticks on my whiteboard, you can replace it using a neodymium magnet, and it's really strong. I mean, to separate it, you need your fingernail tool. It's really fun, but it is really strong. A tiny, tiny coin is gonna slam into the steel like that. So neodymium magnets, very powerful, and it needs to be close though. It needs to be close to the stator. So it's that's why it has to be here. And then you have this tiny little steel holding it back, and it causes a lot of. It becomes a bottleneck to the performance.
Why they arrange magnets in front of magnet motors. This I learned it's called interior permanent magnet synchronous machine. We're going to talk a little bit about that later. Induction motors.
In fact, Tesla had to come up with a spatial way to wrap this rotor with a carbon fiber. Okay, it's because it's one of the strongest material with the most compact structure. And so they actually wrap it with carbon fiber to constrain the rotor from exploding in high speed. So a permanent magnet synchronous motor is very powerful and can rotate at very fast RPM. The only limitation is that little structure there. So if you can fix that, then you fix it.
Again, these are both electric motors. And they both
Now, these are induction. Okay, it's also called a squirrel cage motor because it is also kind of, I mean, if you look at it, it's kind of similar to the hamster cage, right? But they are not, what do you call that, wound wires. So these are not coil, these are just copper. That's the aluminum version. It's a copper version, better, more expensive. But it's just a piece of steel that now creates the eddy currents, induced currents around.
Kind of stator, where it doesn't have any line stator, you can use strand wound or power wound.
And that's the stator, right? The stator have the three-phase different arrangement coils, different many poles on that stator.
Both permanent magnet motors and induction motors use the same kind of stator. But the difference is the rotor, and induction motors don't have any magnets. So instead,
So the stator is very similar between PMSM and induction, but the rotor is different. The rotor is like this for induction, and for permanent magnet is that this one. Okay.
called rotor bars. And then at the other end, all the bars are shorted together with a ring. They form a circuit. And in some cases, when I remove all the steel, you get something that looks like this. And we've been calling this in motor industry the squirrel cage. And so induction motors are sort of rings. So you can go to physical differences between both of these DC motors inside the motor.
Okay, I think that's all I want to show you here.
So you have the stator, and you put a permanent magnet rotor into the stator. Then the magnets want to try to follow the magnetic field around. So if I
He also talked about efficiencies. These two.
electric vehicle applications, and so that's why permanent magnet motor, this alone is why permanent magnet motors, especially in this interior permanent magnet synchronous machine, is usually the choice to go with.
Okay, let's talk about this. Induction motor versus permanent magnet synchronous. Higher torque, right? Higher torque, higher efficiency. I mean, what else can you ask for? You got higher torque and higher efficiencies. More expensive. Higher spin loss. Now, this is a problem. So that is a problem because then, what about highway driving? High speed for a long time. This is where the induction motor wins. Okay, so lower spin loss. Lower spin loss. It can literally rotate and just float. Really nice. But the permanent magnet, even if you're not putting power into it, just the fact that it spins will create some drag. Okay, but because of the differences in performance, in the end, the permanent magnet still wins, especially if you do a lot of city driving. So if you do a lot of city driving, in the end, the efficiency wins over induction, even though you do have some spin loss. Okay. Now, if you do very rare city highway driving, then definitely the PMS will win.
So those are the advantages and disadvantages of the permanent magnet and induction motors. I put up here the synchronous versus asynchronous. The way we make torque, as we call it, is we use.
So yeah, so here, right? I mean, you literally cannot turn it off. Now, here's the efficiency map. I think I have a zoomed in version of this. Here. Okay, so the other aspect is that when you talk about efficiency, efficiency is not constant in all RPM range, okay? Apparently, the permanent magnet motor is actually more efficient in lower RPM. And so this is the highest efficiency zone here, right? So this is where your city driving is, basically, right? Low RPM, low torque, so stop and go driving is right here. Now, highway driving will be high RPM, low torque. So this is where the induction motor actually wins. Now, do you have to pick one or the other? Not if you have the money. So if you do both, then you can actually think about it, an optimization algorithm, right? If you have induction in the front and permanent magnet in the back. So which one you activate can depend on your speed, right? So you can actually do permanent magnet most of the time and then switch to an induction when you're doing constant speed highway driving. Really nice. But the permanent magnet motor, by the way, the flat torque is actually a little bit more. So you can go higher RPM still with the flat torque. Feels really nice. I mean, this is part of, a lot of people switch to EVs just because it just feels better. It's just no other way to replace that feel of having a linear acceleration. So this is kind of the summary between PMSM and induction motor. Okay, efficiency is high, induction motor lower, cost is higher because you need these rare earth magnets. Induction motor is just copper. Drag is always present in permanent magnets. In induction motor is minimal, it's just air bearings. Torque at low speed is excellent. You get off from zero, launch really nice. And so this is what they use for the primary drive, and induction is just mostly secondary drive. And we talked about that. Now, let's talk about inverters a little bit here. Because if you think about the traction motor system, you have the battery management, you have the inverter, and you have the onboard charger. We'll talk about charging some other time. So this is what we want to discuss a little bit. This main inverter basically converts DC into AC, but it does a little bit more than that. Primary functions, of course, is motor control, forward and backward, you know, holding on a hill, which I also love with EVs. You don't have to wait for the torque converter to bite in, right? Because you can let go and it still holds still. You press on the pedal, it goes up a bit. A really good control. But that's the job of the inverter there, right there. It's a very, very complex control there. Generator, meaning regenerative braking, it needs to charge back. Secondary function, some battery warm-up. So startup at cold condition, you do want to heat it up to a certain point. Torque vectoring actuation, again, left and right, which one? The DC to DC charging is handled by the inverter because the onboard charger is only for AC to DC. So the difference, I think it's a type 2, the most common in Indonesia. So type 2 is like this, the charging port. So this, it has both, right? So like that. So this is for the AC charging. This is for the DC fast charge. So it's basically, if you plug in AC, then your car, so the small charger is not even a converter from AC to DC. The conversion from AC to DC happens in your car. So in the car, it has an onboard charger. So if you think about it, the charger for AC charger, the slow charge in your home, right? The slow charger, slow meaning up to 7 kilowatt. That would be called slow charging. Anything above 7 or 11 kilowatt is called a fast charge. You get up to 320 kilowatt. I think the Living World Mall has a 320 kilowatt. But 120 is also pretty fast. It's already pretty fast. So you can get like, 70% in 15 minutes. 10 minutes. 320 you can get up to like 8 minutes off from 30 to 70. It's damn fast. I think BYD, last time I saw they came up with something even faster. It's crazy. But anyways, if you look at the Type 2 charging port, so you got the AC charge, you got the DC fast charge. Only two big connectors. Because imagine the amount of current you're handling with these. So the cable is also like this big. You're like carrying a snake around. So you got the onboard charger. Now, this has to be handled by the inverter, the DC to DC conversion, because your battery is a high voltage battery, like 400 volts or 800 volts. Okay. Now there are some related functions also maintained by this inverter. But anyways, the traction inverter handles control and power. And if you split that up, basically the electronics kind of separate for these two, right? Control electronics is electronics. It's like low currents. I mean, it's like a brain, like the CPU. The power electronics is how it handles all this conversion. So if you look at a traction inverter, it handles a high voltage, and also you need a converter or a buck boost in a way, right, into 48 volts or 12 volts. Traction motor operates on like 400, 800 volts. So high voltage. Power steering usually works on 48, some 24, but a lot of them are 48 volts. And then you got your accessories. For your air conditioner, it also uses a electric compressor. Okay, so you have the onboard charger. You got the DC to DC converter. You still have the small car battery, even in EV, to operate your accessories. But it does get charged by the main battery too. So you do have all these different modules inside the main inverter, right? They do the conversion basically with switching. If you think about power, you do learn this, right? In power electronics, yeah, the conversion. If you want to convert AC to DC, you do what is called a rectifier. If you want to do inverting, then you're going to use these IGBTs. I forgot what they stand for, but it's basically switches, very fast switches, and it can handle a lot of current. So how do you then do this switching? I think I have an animation I want to show you.
For that. If we open and close these in pairs, then we can use AC electricity. So, if we were to close switches 1 and 4, then the current flows in one direction. And if we then open these and close switches 2 and 3, we get current flowing in the other direction. So we can use the controller to automatically do this again and again and again. If we did that 120 times per second, then we would get 60 Hz electricity. And if we did that 100 times per second, then we would get 50 Hz electricity. As we have a low voltage input, we're going to get a low voltage output. To reach the 120 volts or 230 volts required to power our appliances, we will also need a transformer to step up the voltage to a useful level.
So we are on 50 Hertz, the US is on 60 Hertz. And then you have to do a transformer to step it up. You need to.
When we look at this through an oscilloscope, we get a square wave in the positive and the negative regions. This is theoretically AC because it reverses direction. But it doesn't really look much like an AC sine wave. So how can we improve this? Do you remember earlier in the video when I said we can open and close the switch at different speeds and durations to change the waveform?
You remember PWM? Explain to me what PWM is.
Switch ventilation.
That's the acronym. But what does it do and why do we do it?
It's like the heartbeat of the system, I guess, or the current, something like that.
Okay, so you have pulses, obviously. But why are we doing it? So let's say you have a motor, a DC motor. Okay? You want to excite the DC motor. Plus, minus. So of course, what you can do is basically hook this up to a battery, right? And just run. Turn it on. Turn it off. Okay? So that's like a DC voltage or current here, right? Now, why do we, when we do PWM on a DC motor, and I do this on, off, on, off, on, off, but do it very fast, what happens?
The output power is being controlled by the turning on and off.
Is less, right? We are actually throttling. So instead of running 100%,